Okay, pre-calc students, this is our Unit 9 review on limits, and in this picture here it's a little blurry, so I'm trying to clarify that we have points at -2, -3, and we have another point at 3, 1, and then we have empty dots at -2, -1, and at 3, 2. So now that we can see the picture more clearly, we can answer these questions. So the first one is the limit as x approaches 1. So 1 is right here, and as we approach 1 from the left and as we approach 1 from the right, we're approaching the same value right here, which seems to be 3. So that would be our answer. The limit as x approaches 3 from the left. So here is 3, and as we approach 3 from the left, we're getting closer and closer to the hole here at 3, 2. So the answer here is 2. This is the y value that we're getting close to. The limit as x approaches 3 from the right. So here's 3 again, and then we're going to go right of 3, and as we approach 3 from the right, we're approaching this hole down here at -2. It's okay for a limit to be a hole. So the limit as x approaches 3, well, we need to consider 3 from the left and 3 from the right, and since they're not the same number, we need to say that the limit as x approaches 3 does not exist. F of 3 is asking what is the defined value of y when x equals 3. So we need to go to where x is 3 again, and we need the filled in value right here, which is 1. The limit as x approaches -2 from the left. Here's -2, and as we approach -2 from the left, we're getting closer and closer to the y value of -1. The limit as x approaches -2 from the right. As we approach -2 from the right, we're getting closer and closer to the same y value of -1. So because the left limit and the right limit are the same number, we can say the limit as x approaches -2 is -1. However, f of -2 is a different number. That is the defined value. So when x is -2, you see the filled in dot here at -3. Okay, we have a new graph for problem 2. So let's look at these limits. The limit as x approaches 3. So here's 3, and as x approaches 3 from the left, we seem to be going to positive infinity, and as x approaches 3 from the right, we're going to positive infinity. So since that's the same, we're going to say that the limit is positive infinity. The limit as x approaches 7. So 5, 6, here's 7. As x approaches 7 from the left, we seem to be going to negative infinity. And as x approaches 7 from the right, we seem to be going to negative infinity, so this answer would be negative infinity. The limit as x approaches -4, let's see, 1, 2, 3, -4. Approaching from the left, we are going to negative infinity, and approaching from the right, we're going to negative infinity, so this is also negative infinity. The limit as x approaches -9 from the left. So here's -9. We're going to go left of -9, and we're approaching it, and it seems like we're going to positive infinity. And the limit as x goes to -9 from the right, that one seems to go to negative infinity. So the question they don't ask is, what is the limit as x approaches -9? But since one's going to negative infinity and one is going to positive infinity, this one would be a does not exist. In 3, we're going to sketch a graph of the function to find out for what values of a the limit as x approaches a of f of x exists. So the first one's a linear function. It's the same as -x plus 2. So we're going to start at 2. And we're going to do a slope of -1, down 1, over 1, down 1, over 1, and that goes all the way across the page in both directions. You can go this way as well. And now we only want if x is less than -1, so we're going to erase the part we don't want. Here's -1, and less than, but not equal to, so we want an empty dot at -1, and then we want to go back. This is another linear function, y equals x, which is 1x plus 0. So you start at 0, and you do a slope of positive 1. So this is going to look like this. You can go backwards as well. Going backwards will put you here, here. But we only want this line from -1 to 1, so I'm going to erase the parts I don't want. And I just want from -1 to 1. It says equal to -1, so I can use this dot right here at -1, but not equal to 1. So I want an open dot there, connect those, and I see one more point I need to erase down here. The last one's a quadratic function, and it's shifted right 1. So normally your vertex would be at 0, 0, but now your vertex is over here. I'm going to change colors for this one. Right 1. So when I shift right 1, that's my new vertex. The parabola has a point that's over 1, up 1 on both sides, and it has a point that's over 2 and up 4 on both sides. I don't think I'm going to be using this left side, so I'm not going to do that one. It also has a point that's over 3 and up 9. And it has one on this side too, but I only want the x values that are greater than or equal to 1, so some of these I can erase. I'm not going to need this one right here. And I do want the one at 1. So it says greater than or equal to 1, so I need to keep the point here at 1, and I'm going to go this way. Alright, so I need to find out where the limit exists. Well, basically the limit exists everywhere on this line until I get to the point where I have to jump down here. And it exists everywhere on this line until I have to jump down here. So I have 2 points of discontinuity, so I'm going to say the limit as x approaches a of f of x exists everywhere except when a equals, let's see, right here, -1, and a equals, over here, this is +1. Alright, let's turn the page. Okay, on the next page we have graphs for the functions f and g, and we're trying to evaluate the limits. So if I want the limit as x approaches 2 of f of x plus g of x, I can find their separate limits and add them. So as x approaches 2 of f of x, my limit is here at 2. And as x approaches 2 in g of x, my limit is here at 0. So 2 plus 0 gives me 0. The next one, the limit as x approaches 1 of f of x is 1. And the limit as x approaches 1 on g of x is also 1. Oops, it's not 1. Because as you approach 1 from the left, you have a different value from 1 from the right. So this limit at 1 does not exist. So if you have 1 plus does not exist, that total is just does not exist. Oops, and I'm going to go back to a now because 2 plus 0 obviously equals 2. Alright, the limit as x approaches 0 of f of x times g of x. So here is 0 on f of x, and my limit from the left, my limit from the right, those are both 0. For g of x, the limit as x approaches 0 right here, well, it seems to be less than 1.5, but the exact value is not important because 0 times anything is going to be 0. So let's estimate it at 1.3, and our answer is going to be 0 regardless. The limit as x approaches -1, so -1's down here. On the left side, it seems to be -1. And on the right side, it seems to be -1. So the limit as x approaches -1, let's see. I get -1 over 0. Well, -1 over 0 is an undefined value. So because f of x over g of x is undefined, we're going to say that this limit does not exist. The limit as x approaches 2 is 2 on f of x. So let's see, f of x is 2. And then it says x cubed, so x is of course 2, so that's 2 cubed times 2, which should give you 16. And the limit as x approaches 1 of square root 3 plus f of x. So as x approaches 1, your y value is also 1. So I have the square root of 3 plus 1, the square root of 4, which equals 2. Alright, so now we're going to find some limits algebraically. A lot of these are going to require factoring. So the first one, we're going to find two numbers that multiply to negative 12 and add to negative 1. And those factors will be x plus 3 times x minus 4. Sometimes you can get a hint from the bottom factor because you know that we're going to try to cancel that factor out. So x plus 3 and x plus 3 cancel out. I'm left with just x minus 4, and now you want to substitute in the negative 3. So I have negative 3 minus 4, which gives me an answer of negative 7. The second one, again, all of these, you can try plugging the number in directly first to see if you get a value, but the problem is, in most cases, you're going to get 0 over 0, so you need to do something else. So we're going to factor again. On the numerator, I need two numbers that multiply to negative 2 and add to 1. So I'm going to have x plus 2 times x minus 1. And then the denominator, two numbers that multiply to positive 2 and add to negative 3. So I have x minus 2 times x minus 1. So these are going to cancel, and now you substitute in your 1. I have 1 minus 1 over, oops, I canceled the wrong ones, didn't I? Let's try that again. So in my numerator, I had x plus 2, and then this is x minus 2. So the ones that cancel are the x minus 1s. So now when I plug in my 1, I get 1 plus 2 over 1 minus 2, which is 3 over negative 1, which is negative 3. Alright, in 7, if I substitute 0 in directly, I'm going to get the square of negative 5, which is 25, minus 25 over h. So what I'm going to do is I'm going to expand this binomial. I'm going to multiply h minus 5 times h minus 5. And I get h squared. Minus 5h makes minus 10h. Negative 5 times negative 5 is positive 25. And minus 25 over h. So the 25 minus 25 cancels out, giving you h squared minus 10h over h. And then what you need to do is factor out the h as a common factor. So h times h minus 10 over h, and now these will cancel. And now I can substitute the 0 in to get my final answer. 0 minus 10 equals negative 10. In problem 8, you need to remember your pattern for a cubed minus b cubed. A cubed minus b cubed is a minus b times a squared plus ab plus b squared. So when I factor this x cubed minus 1, remember 1 is the same as the cube of 1. So everywhere I have a, I'm going to put x, and everywhere I have b, I'm going to put 1. So this becomes, not a, but x. This becomes x minus 1, x squared, plus 1x, which is just x, plus 1. My denominator is difference of squares, which is a minus b times a plus b. So my factors are x minus 1 times x plus 1. Now you can cancel out your factor of x minus 1. That's what was causing the trouble with the 1, giving you 0 over 0. And if we plug in 1 now, we should find our answer. I have 1 plus 1 plus 1 over 1 plus 1, which gives me 3 over 2. Alright, and then the next one, number 9, this is where we need to multiply by the conjugate. So the conjugate of a minus b is a plus b. So we're going to multiply times square root 2 minus t plus square root of 2. And the same thing in the denominator. The reason we multiply by the conjugate is because that way the middle terms will cancel out, giving us something nice and simple. So on the top, square root of 2 minus t times square root 2 minus t is just 2 minus t. And then your middle terms both cancel out, giving you nothing there. And now I have negative root 2 times root 2, which gives me minus 2. In the denominator, you want to leave this factor, so leave the t out. And then we have square root 2 minus t plus square root 2. So on the numerator, the 2 and the minus 2 cancel out, leaving you just negative t. And now you can cancel out negative t divided by t is negative 1. So now I have negative 1 over square root 2 minus t plus square root 2. So now's a good time to substitute in. We substitute in 0, and we have 1 over square root 2 minus 0. Oops, still in my denominator. Plus square root 2. So basically here I have 2 root 2 in my denominator, and then I'll have to rationalize. 1 over 2 root 2, multiply times root 2 over root 2. I get root 2 over 2 times 2, which is 4. Okay, and in the last problem, this is a transformation of your function of square root of x over x. So you can see it shifted right to, which means the way the graph would look is 1, 2, and 1, 1. So you would have an open dot here, and you would have an open dot here, and the graph would look like this. So you can see as you approach 2 from the left and from the right, you're approaching different numbers. But if that's not something that you remember, you can also do this algebraically with a table of values. So I can put in numbers for x and find out the y's. So if I plug in, let's say 2.5, I get 2.5 minus 2 is 0.5, 2.5 minus 2 is 0.5, and that gives me 1. If I plug in 3, I get 1 over 1, which is 1. So on the right side, I seem to always be getting 1. On the left side, I can choose numbers less than 2, so I can choose 1.5, which gives me negative 0.5, absolute value 0.5. So 0.5 over negative 0.5 is negative 1. Or I could plug in 1, and I get 1 over negative 1, which is negative 1. So you can then see that on the left side, you're getting negative 1. So now you can see that as x approaches 2, because you get different numbers on the left than you get on the right, this just does not exist. Alright, in 11, it says evaluate each of the following limits if they exist, then sketch the graph. So the idea is that you can actually figure out these limits without sketching the graph. And let's check and see what's going on with those. So the limit as x goes to infinity. This is what's happening when x is greater than 2. And this is a linear equation, negative x plus 8. So it has a negative slope. So the end of your graph is going to be a downwards line. And so because it's pointing downwards, as x goes to infinity, your y is going to negative infinity. The limit as x goes to negative infinity, well, this is happening here when x is less than 0. This is a line with a positive slope, 1x plus 0. So this line's going up like this. But the question is saying what's happening on the left side, and as x goes to negative infinity, the y goes to negative infinity as well. The limit as x approaches 3. So as x approaches 3, that's going to be this part of the function here when x is greater than 2. And because it's linear, it's continuous everywhere. So I can just plug my 3 in, and I get 8 minus 3 equals 5. The limit as x approaches 0, that is when my piecewise function breaks from one piece to another. So I need to double check that the two sides match up. So the left side, I get 0 in for my x, and I just get 0. And on the right side, I put 0 for x, and I get 0 squared, which is 0. So because the left side and the right side both equal 0, your answer is 0. And down here, it's labeled b. Let's call it e because we've already done problem b. The limit as x approaches 2 from the right, so that's the values that are greater than 2. So we're going to use this function, negative x plus 8. So if I substitute 2 in, I get negative 2 plus 8, which is 6. So this answer is 6. So now let's look at the graph. The first function, y equals x, so that's going to be this one where you start at 0 and you do a slope of 1. And I only want this one if x is less than 0. So less than means an open dot, and less than 0 going backwards. And let's erase the extra points. Alright, the second one, x squared is between 0 and 2. So we're going to have the right side of our parabola, and the parabola would normally have a point here, but we're not including it because x does not ever equal 0. We're going to go over 1 and up 1. We're going to go over 2 and up 4. And we have a closed dot here because it says x can equal 2. So we're going to go like that. And then the third function, negative x plus 8. So I need to go up to 8. 1, 2, 3, 4, 5, 6, 7, 8. And it's not equal to it, so I need an open dot. And I need to go down with a slope of 1. But now that I think about it, that's not where my open dot's going to go. My open dot is going to go when x is at 2, so that's going to be right here. And my line goes this way, but I want to erase the stuff back here because it's only for when x is greater than 2. Alright, so that's the end of page 2, and if you want to see the other pages, you'll move on to the second video.